Okay, rock and roll. Yeah, we'll keep going here. Last time okay, let's do it this year. Okay, so last time we were dealing with a mirror, and then stuff cut out on us, and so I called it quits for the day. Just to remind you of where we were, we had, we went with a concave. Okay, there we go. Now I got we went with this idea about, okay, we have a optical axis like this, and we've got some sort of spherical or concave mirror. If I can draw it, okay, that's really bad. Let's try it again. Okay, something like that. We put a focus in. It's not supposed to be wavy, but I swear I drew it out so you have a clean picture at the very end. Okay, so something like this, and then we decided to set, this is the focal distance, and then we decided to set our object beyond the focus, somewhere like right here. Good gravy. Man, why is it so hard to draw straight? There we go. Someday, I'll just have to get an iPad like Dr. Pretorius. Then I can actually see while I'm drawing. Yeah. Okay. And then I said, well, we have 3 rays that we want to consider. If we're dealing with a mirror, we have 3 rays that I want to consider. What's one of those? This is always good to remember. So you don't have to memorize all the situations, but you should memorize what the rays are. What rays do I need to draw in order to get an idea about what's going on? Yeah, give me one of them. Let's say, and this is the optical axis, by the way. The symmetry axis, if you will.
The one that goes from the top of the object parallel.
And so from top of the object, parallel to the optical axis, strikes the mirror, and where does that ray get directed to? To the focal point. So this one goes through the focal point. Okay, and keeps going. Good. How about another one?
From the top of the object through the focus.
Top of the object through the focus. Hits the mirror. Parallel to the optical axis. Okay. So already, and this is where it cut out on us, I said, already you've got an idea about where the image should be. Okay. Where the intersection of those 2 rays are, that's where the image should be now. Okay. Now, I always encourage people, when you get good at it, 2 is usually enough, but you should always do a third. Because, if you do 2 and one's wrong, then how do you know if you have 2 measurement apparatuses and one's wrong and one's right, how do you know which one's actually wrong? Right? We've already learned our lesson, right? You throw out the older one and count the newer one as being the right one. No, that's not right. When you finish with 2, you should get 3, right? So you need a third one. So the third one, which we want, and okay. So what we'll do is for the mirror, I said, well, if you have one that comes in normal to the surface, and please forgive me, this is a crappy mirror, right? Ideally, if I gave you a really nice one, it would be something like you go normal to the surface and it should come back directly. Okay, now I can't draw. Let's try that again. Here, if I get the nice curved mirror, there we go. You have something going from the top of the object, it gets normal to the surface, perpendicular, and it should reflect all the way back. And if okay, you get the idea, hopefully. See, if I say it louder, then that means, I've seen this study, the louder a professor yells, the easier, the more learning happens. No, I don't know. Yeah. I'm just making stuff up, but you guys aren't contradicting me, so I figure it's okay. Okay. So 2 gives you an idea, 3 confirms it. And so what you end up with is an image. Again, if you could do these straight lines, what you'd end up with is an image roughly here. Based on kind of what I've set up here. Is that what we had last time? Roughly speaking, We had an image that's further away from the mirror than the object. Is that right? Yeah. I know it cut out on me. I lost all that notes from Wednesday. Okay. So first of all, you now have an idea about where the image is located. It's further away from the mirror than the object, number one. Number two, upright or inverted? Upside down or right side up?
Upside down.
Upside down, right? The object starts right side up. After the reflection, the image is upside down. That's why you put the arrowhead on, so you know, right side up and upside down. So it should be further away from the mirror than the object. It is inverted as compared to the object. And also, you notice magnified or demagnified. Is it larger than the object or smaller than the object? Blue arrow compared to an orange arrow. Larger, yeah. So you get an inverted magnified image. Now, if you did this on graphing paper, and you did it with a ruler and you're really precise, you could literally measure the size of the object arrow, you could measure the size of the image arrow, and you could find the magnification just measuring those two. The magnification, in fact, shoot, I gotta remember. The magnification is the ratio of the image height to the object height, if I recall, with an additional negative sign. The reason that negative sign is in there is in case if you have an inverted image, that would be a negative height, and so you flip it to get the positive height. Or a positive magnification, excuse me. Oh, so if I recall correctly, this is the magnification. And you'll have to correct me if I'm wrong. The image height to the original height tells you if it's magnified or demagnified. Incidentally, units of magnification. Good, unitless, right? You're taking a ratio of the heights. The other thing I should mention is that the lenses, mirrors, it preserves the distances. It preserves the ratios. So the ratio of the heights should also be equal to the ratio of the distances. All right. So, I'm sorry, labeling. The height, anything I subscript with O to represent the object, and I subscript with I to represent the image. So if I look at the image height as compared to the object height, I can get the magnification. Or if you want, you can look at the distance of the object to the mirror and compare it to the distance that the image is from the mirror. That ratio will be the same. Yeah.
In a concave mirror, is it possible for the reflections to intersect like before it reaches the object?
Yes. Yes.
Because that's what I got mine through my diagram, so I didn't know if that was possible or not.
I believe it's possible. In fact, let's do it in a minute. I believe it's possible. Where'd you put your object with respect to the focal point? I'm sorry? Or is the object further away from the mirror than the focal point, or is it closer? No, that's possible. Yeah, this is possible.
Focal point is closer to the object.
Shoot, what's the relationship? If you are twice the distance away from the focal point, yeah, that's possible. You did that. You've done everything fine. Yeah. So for me, What Isaiah was asking about was more general warning. Don't memorize these. Okay? They are highly dependent on the geometry. So for what I've drawn here, I've got an inverted magnified image. Okay? Isaiah happened to do a situation where, and I have to confirm this, but he happened to draw his object to, this is incidentally, excuse me, this is the focal length. Okay. He happened to draw his, and I'll double check this, Isaiah, but he happened to draw his object so that it was more than 2 focal lengths away. So he drew his object out here, and I believe you get a demagnified inverted image. Okay. So it's highly dependent. It's not only, it's highly dependent on the situation. So don't memorize it. Memorize the 3 rays, draw it in, and that will tell you what situation you have. Magnified, demagnified, inverted, or upright. Okay. So yes, it's perfectly fine. Okay. I was not very careful with where I put my object. I didn't specify how far away to put the object. So yeah, be careful. Oh, excuse me. Okay, now I've got, no, come on, go back one. Other questions? You've probably seen, you should have been playing around with the spoon at lunch, right? Hopefully on Wednesday you're playing around with a reflective spoon at lunch and trying this out. Really far away, you should get an inverted, smaller image. As you move closer, it should get larger and larger and larger and larger and larger. It stays upside down. Okay. And eventually you get to a point, what happens to the image? Or can you see the image? Played around with this before? Maybe you should go and get. As you move closer, eventually what happens to the image? Can you even make out an image? Survey says, no. There's this transition point. As you're approaching this concave mirror, you see an upside down image. Okay? As you approach it, there is a location at which you don't get an image at all. In other words, what does that mean about the convergence of these 3 rays that we've drawn? If you don't get an image, they don't cross. Yeah, good. And I think, sorry, I'm just trying to think about this. Where will they not cross at? Yes, you could probably give me an idea. Where should, if I don't want to form an image at all, where do you think the object would be located such that it won't form an image? Sorry, I'm way off book here, but in other words, where should I put my object if I'm not going to form an image at all? Let's just redraw it. Here's our optical axis. Hopefully that's on the page. Try that again. Here's our optical axis. We'll pretend that we have a mirror. That's a little bit better. Here's my focal point. Where should I put, if I don't want an image to form, where should I put my object? Yeah, let's do that. Let's do that. Let's say between the focal point and the mirror. So let's put our object right here. Let's try that out. Go ahead. Go. Draw in the array diagrams. Draw. Yeah. See where the rays intersect. And I got to do this in my head too. Let's see here. What am I thinking here? here, goes there. This one goes here. Ah, no, what am I swear this should be. Should be something like this. Goes like that. This one goes like this. You should get something like right there. Sorry, I'm having trouble with my third ray. You say it goes like this. I'm struggling with my third. Are you struggling with your third ray? I'm struggling with my third ray, but let's do two of them and then. You got an idea? I'm struggling with the ray that goes through the focus because you're inside the focal point, right? So it's hard to think about what that ray looks like. Yeah. So let's get the other two. What are the other two? One of them. Okay, goes parallel to the optical axis. So we go like this. It hits the mirror and it goes through the focal point. Okay. Let's see, the second, let's see. So we got one right there. Oh, okay. So, yeah, I'm struggling with the other one. Where's the other one going to be at? Oh, yeah. Okay. Let me give you a fourth one just in case. Because I'm struggling as well. Parallel to the optical axis, strikes the mirror, goes through the focal point. We had one that said it's normal to the surface and it reflects backwards, reflects along the same line. Now, the problem with that one is I've drawn this mirror really junky, but normal to the surface will be somewhere around here and reflects back. Yeah. Something like that. Which means we expect our image just based on two rays. Where should our image be? Maybe I shouldn't have done it in orange. Let me get rid of that one. Let's do it in some different color. In green. It would be coming in somewhere, reflects off the surface and comes back. So it goes in and out. So we expect our image to be somewhere like right here. In other words, upright, demagnified. Am I smoking something? You guys kind of see that? And I'll get back to you on this third one, because, right, you're inside the focal point, so then how do you get a ray that goes through the focal point and strikes the mirror? The answer is you can't. Okay. Yeah. Yay, nay, maybe? Have you ever noticed this if you move your face close enough to the spoon? If you're far away, everything's upside down. If you move your face in, it goes right side up. You ever notice that? There's a transition point where you go from upside down to right side up that you don't get the image at all. So it's not inside the focal point. Where's your gut tell you? It's not inside the focal point. It's not outside the focal point. It's how about on the focal point? What happens if your object is exactly on the focal point? What happens then? I'm sorry? It doesn't form an image at all. Yeah. What ends up, sorry, excuse me, there's one other ray I like to think about, and I should have included this one as well. Sometimes I find it helpful to think about the ray that bounces off the optical axis. And because of the law of reflection, it will be reflected, like at the same angle. So you can also think of that one if that helps out. But the other one that's cute to think about, so if we're inside the focal point, we get an upright one for this case. If we were outside, we got some inverted one, magnified, demagnified. But the most interesting one probably happens when you're exactly on the focal point. And what happens there is that at that location, say you bounce off the mirror and you go through the focus, and say if you bounce off the optical axis and come off, it turns out that those rays end up exactly parallel. If you're standing on the focal point, you never actually get all of the rays to converge. Those are just two rays. Let's see here. We said, okay, I can't draw it through the focus because I'm standing on the focus, so I can't get that ray drawn. If I have a truly spherical mirror, what ends up happening is I go to the point that's perpendicular, and that ray will come back off and also be parallel. And I don't know if you've ever noticed this. You start off with it, it's upside down, you bring it closer and closer and closer, it gets magnified, and then all of a sudden it gets fuzzy for a while. Right? That fuzziness that you see when you're bringing the mirror closer, that fuzziness is you're getting really close to the focal point. Oh shoot! You want to do? I got a mirror upstairs. Should I bring a mirror down? Should have brought a mirror. You want to see a mirror? Okay, give me a second. Take 5. Well, take 2. Let me go get a mirror. I should have brought a mirror. Oh, silly me. What am I doing here? Silly bastards. Yes. Sorry, I should have thought about this. Bam! Well, bam! One concave mirror. Look at you. You're all stars. Right? And I assume you see, you're upside down, right? You're upside down, right? Of course, the issue is as I get closer, right? Like, you're still upside down probably. You're getting larger. But at some point, is it, can you see yourself?
Yeah, man.
Yeah, how about
It's kind of hurt.
oh, it's gonna hurt your eyes.
No.
Oh yeah, it does hurt your eyes. Yeah. But you see?
Yeah.
Yeah, it flips, right? Right about there. Where is it flipped yet? No, when does it flip?
There we go.
There you go, right about there. There's the focal distance. Right? You notice it kind of gets painful, yeah, because you get to see all your nice pores and everything, right? Like you get closer and closer and closer. Eventually, I can't tell. Is it flipped yet? Yeah. All right. You see. I mean, you want me to do this for everybody? Right. I love it. The warning. Of course, this is broken here. Caution: this product is designed to concentrate light rays. Emphasis added. Exposure to direct sunlight can cause extreme heat to be generated at the focal point. You can go outside and find the focal. You want to go outside and find the focal point? Yeah, exactly. We can burn some ants, right? Like. Right, yeah, that's it. Essentially, don't take this outside. Anybody got some food? We could cook some food. Right, they use these as outdoor ovens, right? It's just a mirror, They put the grill, and the grill just happens to be located at the focal point. So you put your food there, you cook the hamburger. Huh?
I wouldn't cook a hamburger.
Yeah. Well, I mean, you could do, but they do make these solar, they're called solar grills. Literally, it's just a nice mirror and it focuses the light so that you just cook your food using sunlight. It's like burning an ant, except you eat it afterwards. It's not, sorry? Yeah. Oh, okay. Well, you gotta make sure it's thoroughly cooked. Okay, do potatoes, that's fine.
How hot would it get?
Huh?
How hot would it get?
Oh, no, I mean, they literally make solar grills. So I'd assume that they get up to a couple hundred Fahrenheit. You know. I can do it with the, here. See, the camera can watch it too. Let me know when it flips. Okay, nice. Okay. So there you go. One giant spoon. Of course, you can do it experimentally with this too. Okay, one's already. I shouldn't do that. I mean, Leo was so careless with the mirror that, I mean, he broke an edge off of it. I recommended him highly for playing around with physics demo equipment and breaking it. I was fighting Thanos, I had a reason. Okay. But you can see this too, right? Convex, but you have a concave. You notice something funny about this. We can do the ray diagrams, we'll figure this one out too. Right, but you notice something funny about this one. Okay. I should have done like that. Anybody have some coconuts? No? Right, but you know something funky about this one. Like if I get closer and I get closer, closer. What happened?
It looks the same.
It looks go back. Okay, maybe I just didn't go back far.
I got smaller.
Be it smaller.
Yeah.
Yeah. You see that? This one's different though. Right, the shape. Right, you can get really close and keep going. Right, nothing. Right, no flipping. That's kind of cool. What's going on there?
There's no focal point.
Huh?
There's no focal point.
Yeah. There is a focal point. The issue is that the focal point on this side of the mirror. No, the focal point's actually back here. So we should talk about that as well. The shape of the mirror, the focal point is on the side of the curvature. Right? The curved surface is this way, that means the focal point's over here. Okay. But the reflector side of the mirror is on this side. So that changes what happens with the mirror. Here, as I get closer, you can measure where the focal point is. It's where your image goes away. So when you get your object close to the focal point, all of a sudden it becomes, you don't get an image. Once you get inside the focal point, then you get your image again. This one, there is no beyond the focal point or inside the focal point. Right? The focal point's over here. The object is always on the same side of the focal point, regardless of where it is. And so the image stays the same. No upside downness, no yada. You do that one? This one's a little harder. This one takes a little more practice. And part of the reason for it, say a little harder, it's the same rules. We're going to apply the same rules. But this gives us an extra thing that we have to consider. So is the question so far? Get this plugged in. The other thing I should say, why do I spend so much time on this? Partially, it's because it helps you prevent making mistakes. Okay. Think of it this way. Ray diagrams are to optics as free body diagrams are to Newton's second law. Okay. Ray diagrams are to optics as free body diagrams are to second law. When you get an optics problem that deals with lenses and mirrors, sketch out a ray diagram real fast. Okay. That will help you at least conceptually see what's going on. spend a little bit of time to try to, you don't have to get a ruler out and get it scaled properly, but try to be close on the scaling. So if you're given a focal distance of 1 meter and the object distance is 2 meters, when you do your ray diagram, it doesn't matter where you put the focus, just make sure you put the object twice as far away. Okay? Try to preserve that scaling, or at least be rough about it, and then you'll get a rough idea of what the correct answer is. Then if you actually want the real answer, I'll give you the number, I'll give you the equation later that you can figure it out. In fact, shoot, it's on the, could give you the equation now if I could remember it off the top of my head. There's a relationship, let me double check it, but 1 over the focal distance equals 1 over the object distance minus 1 over the image distance. I think that's right. Now, let me backtrack to make sure it actually is right. Maybe I should have done that. It's somewhere here. It's buried here. Where is it? 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 It's here somewhere. Okay, to be continued. I know it's here somewhere. I just don't remember which slide it's on, so I apologize. So it's going to be something like this. And I can't, truth be told, this one I don't have memorized. I know that's shocking. I don't have every single stinking equation memorized. Optics was never my strong suit, to tell you the truth. I found the ray diagrams fun, but then when I actually, yeah. Anyway, I can't remember if it's 1 over DO minus 1 over DI, or if those are flipped. I can't remember for sure. I think it's this. So I'll have to check my notes as well. Let's do the other mirror. So the issue is here, like we've mentioned before already. Okay. Oh, that was a halfway decent line. Oh, I'm getting better. Okay, let's try that again. Start here, go. You guys are so patient with me. Thank you, by the way. Okay, never say thank you enough. That's the problem. So mirror, the reflective side is over here on the left-hand side, but we're going to put the focus over here. Okay. Incidentally, when the focus is on the quote-unquote wrong side of the mirror, that's what a negative number means. Okay. When the focus is on the other side, so this would actually count as a negative focus because it's on the wrong side of the mirror, if you will, the wrong side, quote unquote. I was just letting you know about that. Okay. So yeah, let's put an object here. Let's stick an object on the reflective side of the mirror. And this one, we have to be careful. Okay. So I'll walk you through this first one. Line parallel to the optical axis. Okay. So the line is parallel to the optical axis, and it strikes the mirror. It should be directed towards the focus. Okay. I'll modify that a little bit. I'll say it's directed along the line of the focus. What do I mean by that? Imagine for a second, I take, and I'm sorry, I know it feels like a lot of little things. It'll come faster once you do it a couple times. All right, so just start practicing it, and it'll come a lot faster. So let's see here. Let's take the line parallel to the optical axis. Yeah. Okay, right there. Okay. Now the issue is, what's your gut tell you the direction that it should be reflected? Once it strikes this surface, what's your gut tell you which way should it be reflected? Does it go straight back? Should I go down? Which way should it be reflected? Because of the shape of the mirror. Should go upwards, right? You could think about it, if I zoomed in on this little piece, you could think of it as a small triangle right there. This light ray is going to come in and it should get deflected upwards. The question is now, how do I determine where to draw the reflected ray? Directly away from the focus. Okay. So imagine now we know that it's going to get reflected upwards. It should go up this way. I will draw it upwards so that the light ray goes directly away from the focus. So let me put a dashed line in here. And so that dashed line, so this ray should be reflected this way. There we go. So it's not, it's not the actual ray of light that goes through the focus. But if you took the projection of the reflection and backtracked it, that would pass through the focus. And so that's why I put the dashed lines in there. If you had no idea where the ray originally came from, you would perceive the reflection as emanating from the focal point. Right? If you had no idea about this incoming ray, if you only saw the outgoing one, you would perceive it as coming directly from the focus. Is that okay so far? What's one of the other ones? Ray, yeah. Going towards the focus, what happens when it strikes the mirror? Parallel. That one stays true. So let's do that one as well. Let's see here. Let's do, I don't know, this color. So again, imagine a line going from the focus to the top of the object. So right about here, and it keeps going to the top of the object. So you can imagine this ray is directed, dashed line, right towards the focus. Once it strikes the mirror, it should come off parallel to the optical axis. Uh-oh. What do you notice about those two actual beams of light? Rid of that. The blue ray and the yellowish ray. What do you notice immediately about those? They'll never cross. You notice that the actual light rays on this side will never cross. That means that if I were to put a photographic plate on this side of the mirror, I would never actually get those light beams to cross. I'd never actually see them in focus. And this is why I do the convex mirror second. There is a place where they would appear to cross. The actual light rays themselves do not. Right? The solid lines do not. But if you were to take the projection of those solid lines, and I put dashes in, you notice that they do appear to cross behind the mirror. If I ignored completely these incoming rays, if I were to say, okay, I'm completely ignorant of where these incoming rays came from, and I just saw the outgoing ones, where would those outgoing rays have appeared to originate from? If I just gave you those rays and you said, oh yeah, they cross where? Not on this side of the mirror. Where do those reflected arrays appear to have crossed or appear to have originated from? Not over here, but right there. Right, you see how the projection of these reflected rays cross right there? If I were completely ignorant of where the original rays came from, if I just saw the reflected rays, I would say, oh yeah, there's an object right there. The image is right there. Yay, nay? And yes, the third ray, the ray perpendicular to the surface. If we did a ray perpendicular to the surface going in, it would strike and be reflected off, and it would appear to originate right there. I'll put the third one in. Now, question. Sorry, the technical term for this is what's called a virtual image. We still use the term image. It's called a virtual image. It's where the reflected rays appear to originate from. Now, the question is, do the rays actually intersect behind here? Do you get light rays back here? No, they reflect off the surface. And in fact, if I put a photographic film back here, I would not actually get a picture at all. Right? If I put a photographic film right here where the image appears to be located, I wouldn't get a picture at all. That's why they call it a virtual image. It's not that the light rays actually physically cross here. It's that they appear to cross there based off of the reflection. So what you're viewing right now, it's the image of the classroom that you're viewing in the mirror is as if there were actually a classroom right here, located back here. Like a little, what is it, a diorama? Something like that. You're like looking at a little diorama of a classroom that's located right back here behind the mirror. But if I actually put a photographic plate here, you don't get anything. A different way to say it is, when your image location is on the wrong side of the reflective surface, that is what we refer to as a virtual image. And you can say things, we can do the same kind of qualitative assessment. For example, magnified or demagnified? Smaller or larger? Based on the ray diagram. Is the image smaller than the original, or is it larger than the original? Smaller. The image is right side up. It's not inverted. And for this situation, because the focal point is behind the mirror, it doesn't matter how close or far you are from the mirror, you always get the same thing. You ever wonder why convenience stores always have this and never have that? You ever notice that? Why do convenience stores not use this? I mean, it's a mirror, it gives you an image. You can't see on the other side of the aisle. First of all, this tends to magnify. This always demagnifies. In other words, you can't see the field of view is smaller when you look at this one as compared to this one. You can see more stuff in this mirror than this one. It's because this one does magnification, this one demagnifies.
I remember in the movies, there's like a shootout or something in a gas station, and the guy like looks up there and sees the show.
Yeah, exactly. Yeah. It's because this one demagnifies, which means you can see a larger image in the reflection. Another one, this one's upside down. This one only turns right side up when you're really close. This one, you'll always be right side up. So you don't have to worry about how close or far somebody is from you, or from the mirror. It's always going to be right side up. And the same thing, like, you ever notice those blind alleys or those blind driveways? Look across the street, you usually see one of these. Same reason, demagnified, always right side up, no thinking, I see, I don't have to like translate in my head or anything like that, I can just see and see where the cars are. Maybe. The downside, you can't create a solar oven with this. Well, you're laughing at me, right? Does this actually focus the rays of light that strike it? Does this actually cause the rays of light that strike the surface to converge at a single location in space? No. I can run around as much as I want. I ain't burning little ants tonight, right? Like,
It's not at night either.
touche. Right, this one does not actually physically focus the light rays. They all actually diverge. Right? They just all seem to diverge from a single location in space behind the mirror, which is why I get the image. But I can't actually physically, this one I need to focus the light with. I wonder if we could, like there's another, we have another one of these that says something about like not leaving black objects near it. Right, like the black objects will absorb more of the light. I wonder if we can burn a hole in a chair or something. How bright are these lights? Okay, I don't know. You say you can't do this at night, but have you ever been on campus at night? There's plenty of light around. Probably could burn some ants. You know? I don't know. I could read the newspaper in my living room without turning on lights. It's kind of weird. Okay, questions so far? Yeah.
So is it sort of like that fish example where it's like your eye perceives how the light comes off and makes the image instead of image?
Yes, exactly. Yes, your eye is, with this rounded mirror, yeah, good. With this rounded one, it's your eye perceives where the rays appear to be coming from. Your brain automatically interprets all of these projections as coming from that location in space. Yes. Which is again why we call, I should have, with the fishing example, I should have called it you're trying to spear virtual fish. It's where the rays appear to emanate from, not really where the object actually is. Yes. You know, go hungry. I'm hungry. You guys hungry? Corey's like, no. What questions? If I recall correctly, I already said, when your focus is on the wrong side of the mirror, you're going to end up with negative focal values. Okay, that just means that it's on the back side of the mirror rather than on the front side. If I recall correctly, you'll get the same thing with the image distance. If you have a virtual image, if you have an image behind the mirror, you'll end up with a negative distance. Oh. And that's, again, when you get that negative number, it just tells you, oh, okay, it's behind. Therefore, it's a virtual image. Stunned silence. Lenses? The rules basically stay the same. Probably about the one big difference about a lens as compared to a mirror. When you're dealing with the mirror, okay, say for example, a convex mirror, the object's on this side, the image is also going to be on this side. With a lens, where's the image going to be? Not on this side of the lens, but on that side. Yeah. Okay. And incidentally, we'll notice sort of a pattern. The convex mirror, you can think of it as the convex, excuse me, this is not convex, this is concave. The concave mirror will feel a lot like a convex lens. The convex lens will feel a lot like the concave mirror. The convex mirror will feel a lot like the concave lens. That should make some sense. A concave mirror focuses light, actually causes the actual beams of light to converge. Well, that will also be done by a convex lens. Similarly, a convex mirror causes all of the rays of light to diverge. That's what actually forms the virtual image on the wrong side of the mirror. The same thing will happen with a concave lens. Light passing through a concave lens will diverge. And so you'll end up with a virtual image, a point in location, a point in space from which those rays appear to emanate, appear to originate from. In fact, you probably already got it. The other, the other small caveat, we are going to start off with symmetric lenses. In fact, I don't really have very much plans on doing asymmetric ones, but we'll see. So I plan on doing symmetric lenses. What that means, so I'll do an optical axis again, and we can start off with a convex symmetric lens. What that means is this front face has some curvature. So there is some focal distance associated with the curvature of the front face of the lens. I will assume the back face of the lens has the same curvature. Now, if you get into optometry school, you know that this isn't the case, right? A pair of glasses lenses, it's not going to be convex on both sides. In fact, more often than not, a pair of glasses, you'll have a convex surface and then you'll have a concave surface. So you'll end up with more like this moon shape. Okay. What that does is that means that the focal points are not symmetric about the lens itself. Okay. No, I'm not going to deal with those. No, let's deal with this. So first thing is, okay, well, we have the surface. You're going to have two focal points. One on the front side of the lens, one on the back side. It is okay, for purposes of this class, we will assume that it's the same distance. So this is one focal length, this is one focal length. Symmetric. Where do you want to put your object? Let's go ahead. What color do you want your object to be? Let's see here. Let's go ahead. I will put an object. So I called this one focal. Let's put the object 1.5 focal lengths away from the lens. So I'm just being, so I just said, okay, this is one focal length. I'll go a half further and I'll just 1.5. Ray diagram rules. Give me one of them. Not all three, just give me one. And of course, the upshot is the first person to speak up gets to take the easy one. Parallel line. I take a line parallel to the optical axis. It goes through the lens. Now notice it doesn't reflect off the lens. This one traverses through the lens. That's the other thing. Right? So I take one that is parallel to the optical axis. It hits the lens and it will be directed towards the focus. What I mean by that is towards the focus on the other side of the lens. So it'll hit the lens and it will be directed through the focus on the backside. Same idea that we use for mirrors, the only difference is momento, por favor. Somebody has decided, oh, Cassie, she's got something going on here. There you go. Sorry about that. Sorry, Cassie, we put out the torch. You've been voted off the island. Okay. First one, parallel line to the optical axis, goes through the lens, gets directed to the focus. What's another one? Same idea from the mirrors.
From the object to the focus point.
From the object to the focus point, and it will go parallel. So we need a ray going from the object through the focal point, and it'll come out parallel. From the object, now I'm going to use the nearby focal point. From the object through the focus, and once it strikes the mirror, it will come out parallel to the optical axis. The other warning I'll give you, use each focus once. There's two of them for the lenses. You use each focus once. That'll prevent you from trying to run a line parallel through the nearer line. I mean, it'll prevent some of this stuff. Like, oh, which focus do I use? This focus, line running through it, strikes the mirror, comes out parallel. The third one for the lens is, and I think I verbally gave this to you, the third one is run it through the optical center, and it should pass through undeflected. So two of them stay the same, parallel to the optical axis, strikes the mirror, goes through the focus. The second one goes through the focus, strikes the lens, comes out parallel. The third one differs slightly from the mirrors. And it's go through the optical center, and it should come out on the other side undeflected. So you just draw a straight line through. And so what do we get here at the end of the day? We get an image that is inverted or non-inverted. Inverted, magnified or demagnified? Magnified. So we get an inverted magnified image. Somewhere, if I could draw a straight line, somewhere right here. Notice those lights, those beams of light physically cross at that location. Okay, so this is a real image. And the lines actually cross. It's not like the projection of the lines cross. It's the actual lines cross there.
Wait, so does that mean that the light hits the back of our eyes inverted?
Yes. Your brain flips it. Yep. I'm pretty sure that's right. That's a good catch. But yes, the image on the back of your eye is actually inverted. It's upside down from what you truly, what your brain perceives is actually received upside down by your eye. But then when your brain takes that upside down signal and reinverts it. Brains are weird. Yeah, but then what does it mean to be upside down and right side up?
Yeah, like that's what I'm thinking.
Yeah, perception is weird, right? Like, I mean, yeah, basically maybe our world is upside down, but we've been born with it and we know nothing different, so we call it right side up, even though it's upside down.
I remember somebody asking, like, is my red the same as your red?
Yeah. Because red is based on the perception of the frequency of light, or the wavelength of light. Yeah. So what you call red and I call red might be actually different, but you know, you've learned yours as red, and if I could show you my red, it might look blue to you. But I call it red and you call it red. There's no way for us to communicate that we perceive different colors because we label them the same thing.
So everybody technically has the same favorite color.
Yes, exactly. They perceive the same color, but we have different labels for it because that's the only color that we've known for ourselves. Yeah. It's a mind warp, right? Yeah. I told my wife that my fashion sense, my matching of colors is impeccable. It's her perception of colors that's the problem. Yeah. Yes, yeah, very good. Other questions? I guess we could do the concave one as well. Might as well just for kicks. Oh, incidentally, I know this seems like kind of okay. Well, where does it? I think the real power of this doesn't really come in when you're dealing with single lenses. But if you know how to do the ray diagram for one lens, you know how to do the ray diagram for as many lenses as I give you. How would you do that? Actually, I should ask that first. How would you do it? If I gave you a 6-lens system, how would you do the ray diagram? How do you eat an elephant? One bite at a time. If you have a system of 6 lenses, take the object, do the ray diagram for the first lens, find the image location. Take that image location as the new object location for the second lens. Redo. Take the image of the second lens, that is now the object for the third lens. Redo. Take the image of the third lens, that's the object of the fourth lens. Redo. You just chain them along. So it might take some time, but once you kind of have the idea about ray diagrams and what you're doing, it doesn't matter if I give you 3 lenses or a dozen. You can chunk your way through and just do the first lens, take that image, take it for the object of the second, and just walk your way through. Yeah.
Would you have to give us all the foci?
Oh, absolutely. Yeah. I mean, like, what is it? At this point, you have the general theory of what you need to do. Now you just need the numbers to do it specifically. Yeah. In fact, like your objective lenses on the microscopes, you like the cheap ones are probably a couple, like $500. But like when I was in my research group at Purdue, my professor said, okay, we need a fluorescence microscope, go out and buy one. I mean, realize that was like, here, Greg, go and spend $30,000 and don't screw up, right? Like I was like paranoid I was going to screw up this purchase, right? Make $50 mistakes, not $1,000 mistakes. So one of the things I was worried about though is some of the objectives, because those little, have you ever had like just the objective in your hand? It is surprisingly heavy. Okay, and the reason it's surprisingly heavy is it's essentially a big thing of glass. Some of those objectives have 8 or 10 lenses in them. Like the more expensive the objective, the more lenses they have in there, is generally the case. So I think like the cheap ones might only have 2 or 3 lenses, but the really good ones might have as many as a dozen. And of course, each lens is, more money, that kind of thing. So, but that's exactly what you do. You can take a series of these lenses, take the result of the first one, plug it into the second, and keep going. Sorry, I talk to the Olympus to rep a lot, like for a long time. Like those lenses, they actually match the lenses. So it's not like they just bulk produce these things and then just slam them together and ship them out the door. What they do is they have, 10 convex lenses, and then they have another 10, and they actually pair them up to give the optimal image quality. So it's not like they just mass manufacture them, they actually take the individual lenses, because the variation in the manufacturing process can affect the image quality. So even though you have a real consistent manufacturing process, there's still some variation, and so they match the lenses. So like each objective is unique in some sense, which is also why it's so expensive. Don't drop them. That's the other one. Don't drop the objectives. Okay. Okay. Yeah, I think we dropped, what was it? The most expensive, I think we spent about 3,500 for one objective. It was a 20x immersion fluorescence objective. So it was optimized for a sample in water using fluorescence, like a green laser. It was a really good objective, but man, 3,500 bucks, like, made me nervous. I don't know. Please don't let this be screwed up. Okay, let's do the other one. I already warned you, the concave lens is like the convex mirror. So I will draw a concave lens. And again, the same idea. I'm just going to do it symmetric with focal points on either side. Same distance. And why don't we go ahead? I have no idea since I'm so off the cuff. Let's go ahead and I'll just put my object, we'll put it like 1.5 focal lengths away from the lens. Just pick a number. Now here we have to be careful. I said we have to use each focus once. And yeah, let's go at it. First one, optical axis. So I'll go parallel to the optical axis. I go through the lens, and the first question. This concave lens, will that cause the ray that comes through to bend towards the optical axis or bend away from the optical axis? Away. Yeah. You can think of this as, if you want, think of it as an upside down triangle. As the light beam comes in, it will bend towards normal. And then as it exits, it will again, it will bend away from normal. So this light ray will bend away. It'll go up. So how do I draw the upwards going line? I think of the focus on this side. It will bend directly away from that focus. So I've used the focus on the left side of the lens already. So that feels a lot like the convex mirror, right? Parallel to the parallel to the optical axis, it hits the mirror, it goes directly away from the focus. Second one, if I go towards the focus and I strike the lens, so I go towards the focus, I strike the lens, I should come out parallel. It's like I'm going towards the focus, it will pass through the focus, it comes out parallel to the optical axis. And again, just like the convex mirror, you notice that for the concave lens, these light rays will not intersect. They diverge on the right-hand side of this lens. Won't be able to burn any ants. But where they appear to originate from, so unfortunately there will be no convergence here. We have to use the projection of these rays of light. Where they appear to originate from is over here on the left-hand side of the lens. So again, pretending that I have zero idea where the original beams come from, I would perceive these two rays as emanating from an image right here. And yes, we could check the third ray as well. For a lens, the third ray goes from the object through the optical axis. so I'm a little off there, but through the center of the lens, and it passes through undeflected. Oops, oh no, shoot, okay, well, life goes on. So here we get an upright, demagnified image, and it's not a real image, it's a virtual image again. It is not formed by the intersection of the light rays, but rather it's formed by where the light rays appear to originate. I have to use those projections. It's because this diverges those light rays. Those light rays appear to originate from an image located here. Chew on that, keep working on it. I will try to have some prettier pictures posted online for you, and we'll keep going. Have a good weekend. Big plans?